from the University of Toronto, and today we are going to present our data-driven solution to agricultural planning in developing countries. We will begin with some background to motivate our study. Food security in developing countries has historically referred to access to food supplies to meet caloric requirements and avoid famine. Agricultural policies therefore focus on staple grain self-sufficiency in order to meet nutritional demand. Staple grain self-sufficiency was a major part of resolving food insecurity problems after the 2008 food price crisis. In developing countries where the economy is rapidly evolving and the middle class is expanding, dietary preferences are also changing, and therefore demand for certain foods is highly dynamic, and policies are slow to meet the changing needs of the rapidly growing middle classes of BRICS. BRICS countries stand for Brazil, Russia, India, China, and South Africa, and our data analysis will focus on these countries. Governments aim to balance and optimize the supply and demand equilibrium, as there is incentive to forecast and respond to changes in supply and demand. Inefficiencies in this system can result not only in direct financial losses, but in health issues for the population, such as malnutrition and child stunting. The problem which our study will address is that current agricultural policies in BRICS countries favor the production of staple grains and do not address malnutrition or growing diet diversification. Our hypothesis is that there is a significant discrepancy between agricultural production and dynamic consumer demand caused by agricultural policy in BRICS countries. Although our data analysis will use data from all of these countries, our model will be applied to China as a sample solution.
Our methodology is in two parts. In the first part, we analyze the food production and demand in the past 50 years using machine learning technique and make a prediction on the next year quantities. We then build a stochastic model for minimizing an objective within a set of constraints. We use data from 5 developing countries and 5 developed countries to identify difference in gap. And we found there's a supply and demand gap for all foods analyzed for developing countries. Specifically, the production is drastically increasing in green products while the demand for meat, vegetables, and fruits are not met. This creates a surplus of cereals, which eventually goes to waste, and a shortage of supply in other categories. As can be seen in the two graphs, the demand labeled with suffix X are all met in US. Only the cereal production is in surplus. However, in a fast-growing country such as China, the demand for dairy and vitamins are rising drastically because people are more conscious of nutrition balance, but the supply is not keeping up. Linear regression fits the demand data for each country and each food type and predicts the future value for next year. Note that although the curve in the graphs above do not seem to be linear, but the linear regression has a capability to fit nonlinear functions through feature space transformation. And mathematics analogy would be to change from Cartesian coordinates to spherical coordinates, so that a nonlinear function has such a circle has linear representation in the latter. In addition, from the regression, we also compute a confidence interval on our predicted demand that accounts for 3 scenarios of the demand. Taking the demand prediction from the previous section, a stochastic model is proposed to tailor recommended supply to accommodate possible uncertainties in the predicted demand. The supply quantity can be viewed as the unknown and the cost of supply as the resources in classic stochastic modeling, where the model represents a set of decision variables that must be taken without full information regarding to the changing equilibrium of supply and demand. In this case, the decision is designed to be actual supply quantity of each type of agricultural product, and the second stage of resource decisions is designed to be predicted demand based on linear regression. Here we formulated the model on 3 proposed scenarios of demand, and the projected demand for each type adjusted to account for surplus and shortage amounts. The benefits of stochastic modeling is that it acts as a hedge against uncertainty by considering all possibilities of demand. Therefore, it generates a balanced production and purchasing strategy across its agriculture types.
So we'll now go over our results. Due to the large amount of data available and to focus our solution, China is used as one live example to demonstrate the optimality of the proposed model. The team has showed two different approaches. One, a net profit approach, and two, a value and food loss approach. For the net profit approach, the net profit is calculated by subtracting production costs estimated using the supply quantity from sales revenue by selling the product. For the value and food loss approach, the value, waste, and food loss can be divided into two situations. Supply produced is greater than the demand and vice versa. In the first case, where supply is greater than the demand, the value of food loss is the difference between supply and demand multiplied by the production cost. If the demand is greater than the supply, then the value of food loss is the lost potential profit, which is the difference multiplied by the unit profit. Using these two methods, we found that the net profit can increase by 24.46 billion to a value of 17.89 billion, and a reduction in food waste of 2.78% can be realized. Therefore, there is significant incentive for governments to understand and predict supply and demand. Inefficiencies in this system can result not only in direct financial losses, but in health issues for the population. In the implementation of the solution could be viewed as a large-scale technical business project, which has many associated costs, especially if it will be implemented on a national level. The costs of the project include IT development, creating a user interface, testing, administration, and the ongoing costs for administration and system maintenance. To obtain an estimate for the IT development costs, the team interviewed the IT department of Deloitte. In comparison to similar projects, a project of this scale would take 15,000 to 18,000 hours per region. This data has been used to estimate our pricing. The actual pricing is shown in this table. Government administration and continuous monitoring of operations would be required. These costs are estimated based on historical ranges for government spending. Serving costs are estimated using historical census costs for the past 50 years in China. For each estimated cost, the upper and lower bounds as well as the median costs are used to capture the range of possibilities. We found an overall expected cost of 12.75 to 18.84 billion. As shown in these tables, in the lower bound cost scenario, the ROI reaches 91.88 and the payback period is 1.09 years. And at the upper bound cost scenario, the minimum ROI is 29.85 with a payback period of 3.35 years. The median case will fall between these two extremes. So in conclusion, the proposed stochastic model generates an implementation-ready solution. We have shown that decreasing inefficiencies in supply and demand is profitable and can reduce food loss and have positive nutritional outcomes. By using this model, the government will have more predictive capacity to make timely policy decisions. However, the model has substantial limitations in its current form. The model uses data provided by the FAO on food consumption to quantify and predict the demand. However, this demand can be inherently influenced by current food availability and cost. Alternative methods such as surveying could improve demand prediction. The current stochastic model is only able to predict one time period, 1 year. Expanding the model for longer time periods could help make long-term predictions. Comparing supply and demand directly could overlook frictional factors such as inflation, consumer price index, and import-export patterns. The impact of these factors would need to be evaluated. Thank you for listening.